This is TMUA 2023 paper number 2. Let's just do it. We get a normal maths question first. Let's just times these dominates together and then put this one over there and this one over there, I guess, would be the easiest way of doing this. Remember, minus into a bracket here. Minus makes a plus. This is a difference to do squares, just makes x minus 36, which is nice. And then if you just times this fraction by 4 over 4, you can make the numerators the same, which means the denominators must be equal, and we'll basically be done with the question. And that was the first one. Done nice and easily. If you have integrals with the same limits, you can just bring them into a single integral like this. And now here is something squared minus another thing squared. So let's do the difference of two squares. It's going to be this minus this in the bracket times this plus this in a bracket. In this bracket, these two ones cancel and you get 2 root x. And in this one, the other two cancel and you end up with 2 over root x. The root x's cancel. The 2's make a 4. And then you just have to integrate and you'll get your answer of 28. Quite a nice little question. Question number 3 then, well, you just need to put them in, right? So just put 1 and 16 in, put 1 and 16 in. 1 to the power 16 is 1, and the square root of 1 is just 1. 1 to the root 16 is 1, so this totally checks out. And this is not a counterexample because it totally works. It does this thing. When you put in 2 and 8, you get this. 2 to the 8 is something, but more precisely, the square root is 2 to the power half, so this becomes 2 to the power 4, which is 16. And now this here is 2 to the power 2 root 2, which is not 16. So this is a counterexample. This middle one here, and then this last one is not, because 3 to the 4 is, what, 81, and then you root it down for 9, or it's just 3 squared when you put a power half here. And this is also 3 squared, so that's not a counterexample either. Just the middle one will be the one that we want to select. For this one here, what is the largest number of consecutive odd integers that are prime? Now, it's very helpful that I know the answer to this question, and it's 3, 5, 7. Sometimes just knowing stuff helps out. So 3 is the largest number of consecutive odd integers that are all prime, and there they are. So when I look at the bottom line of this, I know that he's wrong because he says the answer is 2. So it's definitely not this. There's some error somewhere. Let's have a read of it. There are 2 consecutive odd integers that are prime. Okay, well, I think we can agree with that. That's fine. Now, this second line is not how a sensible person would do it, but there's technically nothing wrong with it. We would really want to write 2n plus 1 in the middle here to represent an odd number, but you could do it this way because for some n, this is fine as long as n is odd. So I don't really have a problem with this, although it's not a very smart way of doing it. Likewise, if n is 1 more than multiple of 3, then n plus 2 is of course a multiple of 3, so that's fine, and so is the next line just the same. And the only other possibility is that n is a multiple of 3. I agree with all of those lines. Now here, in each case, one of the integers is a multiple of 3, so not prime. What if that multiple of 3 is 3? And then it's prime, and then my example here is demonstrating that, right? It's the one that's just a multiple of 3, which is 3 itself, which is prime. So therefore, that's the error. He's just left out the idea that 3 itself could be prime. Draw the sine 2x graph. It looks like this. So it just repeats itself twice until it gets to 2 pi. Now, if we need the integral of sine 2x to be 0 between 0 and some value, we need all the area to cancel out. So the first value of k that will do that is, I guess, 0. You go from 0 to 0, and that's fine. Next value will be pi. If I use k as pi, then this area will cancel, and you get area 0 when you do this. And then next will be 2 pi. The next will be 3 pi, because it goes down and up again, and it will all cancel. And so if k is an integer multiple of pi, I think that's just the things that do this. I don't think there are anything else that do this. And so I think this is necessary and sufficient, because they're just talking about the same list of numbers. So yeah, I think that's all we have to say. Now, this thing here, a to the x equals x, is kind of like saying, when does the graph y equals a to the x intersect the graph y equals x? Now, if we draw those two things, I think I just chose a is 2 when I put this in the computer. You get these two things here. So, okay, so these two things don't intersect. But of course, you can choose a smaller value of a that rises a bit slower and make it have some intersections. That's fine. So it could have none, or it could have 1, even if it's tangent, or it could have 2. Nice little question is to work out what value of a gives you a tangent here at any point. It's not too hard, but it's a nice little question. Anyway, back to the actual thing. Here are 2 examples of the graphs that represent this. Log a of x. Now, log to base a of x is the inverse function of a to the power x. And a nice little fact about inverse functions is that they're symmetrical with their complementary function in the line y equals x. So log to base a of x is going to be symmetrical like this. And of course, if this didn't have any solutions with line y equals x, the reflection is not going to have any either. Right? And likewise, if it has 2 intersections with y equals x, the reflection is going to also have 2, because it must pass through the reflection line at those 2 points. So this will necessarily have the same number of roots as the original one every single time, so that's fine. Now, if you square the x graph, so this is y equals x, if you square it, it becomes y equals x squared, which looks more like this. And of course, this is going to have a solution over here somewhere because it goes back up again. So this is immediately out. That's not going to have the same number. Here's an example where it had 0 to start with, just there, and now it has 1. So, okay, nope. And now this one here, a little bit more difficult to think through, but on both of these two functions here, we've gone from f of x to f of 2x, right, to replace both of these with 2x's. So both graphs have been shifted via a graph transformation of a power of 2 towards the y-axis, or they've been squashed by a factor towards the y-axis, which means if they were separated in the original section, they're still going to be separated in the new graph because they've both been squashed equally far. And if they intersected, they're still intersected because like this point here will squash, but the green and the blue will squash together to this point here, and they'll still intersect. So that will always have the same number of solutions as well. So I think those two will. Number 7, so, I mean, vaguely sensible thing would be to rearrange that into y equals mx plus c. Now, if c over b is bigger than 0, that means positive y-intercept. And if a over b is less than 0, that means also a positive gradient because of the minus minus. But that's a necessary and sufficient condition, I think. Like, that would just make this just do the thing. So we actually don't want that. What we want is a condition that is necessary but won't guarantee the thing actually happens. So let's go all the way down to e. A and c have opposite signs. Now, if a and c have opposite signs, that means that one of these fractions is positive and the other negative. Now, if this is the positive one, that means this is the negative one. And then that will be perfect because the two negatives cancel make this. However, that's not always the case, right? Because this could be the negative one. Sorry, this could be the positive one, which would make the whole thing negative, and this could be the negative one, which means it wouldn't do the thing. But that's exactly what I'm looking for. Like, I'm looking for a condition whereby it doesn't always guarantee the thing, but it is something that has to happen. A and C do have to have different signs because, of course, B has the same sign. If A and C have the same sign, then A over B and C over B have the same sign, and because one of them's got a negative in front, that means they have different signs overall, which means you can't be positive or positive. So I think E is the only one that makes any sense for this specific condition here. Okay, next one, we have an acute or obtuse right angle triangle. So let's draw the obtuse one first, like this. And how many ways can I cut this to make at least one right angle triangle? Well, I could just cut straight up, right, to make a right angle here. Only one of the triangles has to be right angled, it says. So that's one cut. But you could also cut it through the altitude to make right angles here and here. And you could also cut it across, kind of perpendicular to this line to make the right angle there. So that's 3 ways of doing that. Okay, so that's the obtuse version done. And I don't think it really makes a difference if I make this more or less obtuse. I think it's always just going to be this, basically. You can always split the 90 degrees, or the thing that's bigger than 90 degrees, up into 2 different 90s, one with the spare bit on the left, one with the spare bit on the right, and then always do an altitude. So I think that's just always going to be the case. For the acute angled case, where all 3 angles are acute, you've of course just going to have 3 altitudes. And I don't think that's going to change either. So I think there's only ways to do this 3 ways. And I don't think there's anything else you can do aside from that. If at least one of the interior angles of a pentagon is 108, then all the interior angles follow an arithmetic sequence. Now that's clearly absolute nonsense because of, say, this one, where I've just gone down to here and up to here, they add up to 540, but that's not an arithmetic sequence. So that statement isn't true. The contrapositive, now, if you've got a statement that says if P then Q, the contrapositive is when you flip these two over, but then also shove in knots in both cases. So that's very useful to know. So let's just do that. So if not all the interior angles make an arithmetic series, so basically if the interior angles don't make an arithmetic series, then not one of them 108. So none of the angles is 108, then I guess is what we'll say there. So, okay, can we come up with a counterexample to this, or is that just always true? Well, here's one where this isn't an arithmetic sequence, but the angle is 108. So therefore, I don't think that one's true either, because that's just not going on. Found a counterexample. Always about counterexamples, right? It's always about that. The converse of star, now the converse is just when you flip the two things over, so if P then Q. So if the interiors make an arithmetic series, then at least one of the angles is 108. You can actually prove that this is true mathematically. Maybe you set it out like this, where these are the 5 angles. They make an arithmetic series because they increase by k every time. But if you add all these up together to make 540, of course, all the k's cancel, and then has to be 108. So the middle one has to be 108. So therefore, the answer is D, I guess, as well. Number 10, then. So, okay, let's go through this very slowly. This seems like an okay line, just added 4 to both sides. This you're just factorizing, so that's fine too. This you're square rooting. Be careful here, but I think this is fine. For this thing squared to be less than 4, it has to be between -2 and 2, so I kind of understand that. Now this next line is a little bit annoying. If and only if this. Now that's just not true, because if and only if means, basically the same statement. Because you've dropped the -2 less than sign, it's not if and only if, except it actually kind of is in a weird way. Because what it is if and only if is this. Like going from here to here, I've just noticed that something squared -1, the minimum value of that is -1. So this, if we're just making his work a little bit better for a second, we can go from here to here. And then when we add 1 to both sides, we'll get this. And notice that's basically the same thing as this, because x squared has to be positive or equal to 0. So we've arrived at his line here. So actually although it's not written very clearly and not written very well, there's actually, I don't think, anything technically wrong with it. And then this last line is good too. It also helps if you go back to the original thing and maybe factorize it and then factorize it again. You can see this only has 2 roots at root 3 and minus root 3. So therefore less than 0 is in between the 2 roots, which is the answer that they've got. So I think this is all just about fine, even though this isn't written in the best way. Unless I'm missing something, I would have rather gone round this way to get to here. But there's nothing actually wrong with it, and the answer is okay. So yeah, we'll go with that. Question 11, then, we have this theorem that I actually didn't know about, which is cool. And it says, which of these following statements is equivalent? Now, this is the converse of the statement, right, where you switch over the two things. That's not necessarily equivalent to it. Lots of things change their truth when you swap them over like this. Also, if this were true, then we would have just an incredibly efficient way of finding primes. You would just choose k to the power of 2, and then you find your prime. So, yeah, that can't be true. This one here is actually saying the same thing as the one I just crossed out. It's saying that you only find not primes if k is not a power of 2, which therefore suggests that if k is a power of 2, you are going to find a prime, which again, we've just crossed out as a statement that's not true, and it's not equivalent to this one here either. But this last statement is true, because this is what sufficiency means. If something means something else happens, that's sufficiency, right? This thing is enough for this to happen. So it's sufficient for this to happen that this has happened before. So that's just the definition of sufficiency. I've talked about that in previous videos, so go watch those videos if you want to. In number 12, then, we can divide both sides by sine x, as long as we check the case sine x equals 0. And we'll be left with cos squared x equals p squared, which we can square both sides to get plus or minus p. And so sine x equals 0 has 3 solutions in this range, 0, pi, and 2 pi. Cos x equals plus p has 2 solutions, because cos just goes down and up again. Any value of p. Well, not any value of p. I'm actually going to break it down. If p is bigger than 1, it obviously has 0 solutions because cos doesn't go that high. If p is equal to 1, it has 2 solutions because you'd have cos x equals p, or cos x equals 1, or cos x equals -1. Both of those have 1 solution each in this range. If p is between -1 and 1, you get 2 solutions for each of these. So if p is like 0.5, cos will be 0.5 twice in one cycle, and it will also be -0.5 twice in one cycle, which gives you 4 solutions in total, and then it's just the same backwards this way around. Which of the following is true? N equals 3 is sufficient to deduce p is bigger than 1. So if you have 3 solutions total, that means you're getting 3 from here and none from over here. But you could be getting this none. P is less than -1. So this isn't sufficient to conclude p is greater than 1, because it could be p is less than -1 instead. N equals 7 only if this, well, yeah, the only way you're getting 4 is if p is here. You need those 3 from here all the time, and so therefore you end up with 7 in total, so it's going to be 2 only is the true one. X is a real number. Which of the following essentially is sufficient for 3 of the others? So let's just go through these one by one. If this is just the true one, that's not sufficient to deduce this, because this is just saying x could be any positive value or 0. So not sufficient for this. It's also not sufficient for this, for the same reason, because this is just saying x is any value that's positive or 0. It's not sufficient to conclude, it is sufficient to conclude D, because we're in this case. But it's not sufficient to conclude E. So it's only sufficient to conclude 1, so we'll cross that out. It doesn't make sufficiency for 3 of them. If this is true, then that's sufficient to conclude this, of course. It's sufficient to conclude this, because we're in this case. It's sufficient to conclude this, we're actually in both cases. And therefore, of course, it's sufficient to conclude this, because we're also in both cases. But that's 4 things that it's sufficient to conclude. So that can't be the case either. If x equals 0 or x equals 1, that's sufficient to conclude that x is bigger than or equal to 0. It's not sufficient to conclude x equals 1, because x could equal 0 instead. It's sufficient to conclude either of these things, and it's also sufficient to conclude both. So that is 3 things in total. This one, and this one. So that's going to be C is our answer. For 14, I rearranged all three of these things to get these statements. And now what I did was I just said, okay, if two of these lines are parallel, so let's just choose A to be 2 and B to be 1. That means the gradient this is -2. And if I want this one, say, to be parallel with it, I would need, well, B is 1. I need this to be a -2, right? So I need B to be 1 because it is 1, which means I need C to be a half. 1 over a half would make 2. And then we just run with this. Then all three are parallel, except the gradient of this third one is not -2. It's a half over 2, which is a quarter with a minus in front. So that's not true. If two of the lines are parallel, so again, we'll just go with this case. The third is perpendicular. Well, we said this was what, minus a quarter? That's not perpendicular to -2, so no. The third is parallel to y equals x. Well, minus a quarter isn't, so no. This is doing a lot of work here. It was nice. And perpendicular to y equals x, well, that would be a gradient -1, which is no. So this just simple counterexample got rid of all this. 4. Next, we'll do if two of the lines are perpendicular. So, okay, let's just make A2 and B1 again. And this time, to make this perpendicular, this has gradient -2. We're going to need to make this one positive a half. If B is 1, that means I think I need C to be -2, because 1 over -2 with another minus makes a half. So it'd be a half here and -2 there, so that's good. Let's just check out what happens with the last gradient. It's going to be -2 over 2, which is gradient 1, which is parallel to y equals x. It's definitely not perpendicular to y equals x, so I can cross this one off. I haven't actually concluded that it's not e, but the chances of me picking a random counterexample and just getting this by accident is so low that I'm just going to underline this and just go with it. So yeah, number 15, there's just an explanation of how standard form works. So that's kind of boring. And then it says which value is this. So okay, I mean, and this is in base 2, right? So this is not base 10, it's base 2. So we need to just do this thing to it for a bit. So the first 1, 2, 3, 4 digits are just going to be this based on how this works. The next 4 digits are also 0, 0, 1, 1, but we're further down the powers of 2. So it's going to be this. And then after that, you're going to have another lot of them. And then after that, it just keeps going. Now, what I could do here is I can, from this row here, I can factorize out a 2 to the -4 to make it look the same as the previous row. And from this row, I can factorize out a 2 to the -8. And now it's the whole thing is just this thing, brackets, 1, plus this, plus that, and so on. And now I can actually evaluate this thing as well, right? So I've just factorized out this entire big object here. Finally, I'm going to evaluate this, so it just goes away. This is an 1/8 plus a 16th, which is 3/16. And now this here is just a geometric series to infinity, with a being 1 and r being 2 to the -4. So let's put that into that formula, a over 1 minus r. 2 to the -4 is 1/16. So this is 15/16. This goes to the top, cancel the 15s, sorry, the 16s, and you get 3 over 15. I must admit, for an embarrassingly long time, I was annoyed that I couldn't find 3/15. I'm just being honest, I was annoyed that I couldn't find 3/15 in the answer list, and actually checked through my working all the way through before realizing that 3/15 is indeed 1/5. That's, sometimes these things happen, and you just have to own up to them, it's just a thing that happens. Anyway, for this one, A and B are factors of, or multiples of 7, right? If they have a highest common factor of 7, that means they're both multiples of 7. The first 5 terms of this Fibonacci sequence just go A, B, A plus B, because you add these together, A plus 2B, because that's what these two added together are, and then 2A plus 3B, and then 3A plus 5B, and so on. U to the 2023 is therefore going to be some number times A plus some number times B. But if A and B are both multiples of 7, that means that you can just factorize out the factor of 7 in both A and B, and this will definitely be a multiple of 7. So that's definitely true. If U1 is not a factor of U2, then U1 is not a factor of UN for any of these. So counterexample, let's go with 14 and 7. 14 is not a factor of 7, but they do have a highest common factor of 7. If we just continue this for a bit, we'll find that U1 is a factor of U4. So therefore, this is not true. The highest common factor of this and this is 7. Again, this took a little bit more effort, but I found a counterexample, 21, 14. So they both have a highest common factor of 7, so that's fine. And if you just do this, the fifth one, we can use this just to get there straight away, is 2 lots of 21 plus 3 lots of 14. Now 14 is 2 times 7. So pull the 2 out and put the 3 in, and you get this. And then this is 4 lots of 21. which is and that's the fifth term. And so the first term and the fifth term have a highest common factor of 21. So therefore, this is also not true. So 1 is the only one that is true. Counterexamples is the name of the game. There's a very similar question to this in step assignment, like 3 or 4 or 5 or something. It's very early on. All we need to do is, the golden rule is that you do not integrate mods or floors or ceilings. You just draw them. So in between 0 and 1, the ceiling of x is 1. So in between this thing here, this is just 2 to the power 1, which is 2. So it's just a line at 2. In between 1 and 2, this is 2 to the 2, because all of these numbers round up to 2. 2 to the 2 is 4, so you just have a line at 4. And you keep doing this until you get all the way to 98 and 99, when up to 98, you're doing 2 to the power 98, and up to 99, you're doing 2 to the power 99. This is kind of like a logarithmic scale, I think, is what I'm going to argue here. But anyway, now the integral of this between 0 and 99 is just the sum of all of these areas. So it's going to be 1 times 2 plus 1 times 2 squared plus 1 times 2 cubed, and so on. I don't need the ones, all the way up to 1 times 2 to the 99. Don't need the ones, obviously. And now this is just a geometric series with A2 and B2, sorry, and R2. And there are clearly, how many of these? Well, there's just going to be 99 of them, right? Because there's 1, 2, 3, 4, up to 99, so there's 99 of them. We can, of course, just put this in the formula, which is this, which is going to be this. This is just a 1. Expand this out, and we end up making it look like f, which is the correct answer. For 18, I'm going to draw this. So this is a quartic function. So for it to have 4 distinct real roots, it's got to look a bit like this. It can't look like this, because that has no root roots. And it also can't look like this, because that only has 2. It's got to be the middle one. So what do we notice? Well, we kind of notice that C looks like it basically has to be positive. Because if C is negative, you're not reaching high enough with the middle stationary point to create 4 roots. So I think it's one of the C is positive ones. So it's got to be one of these two, unless C is positive is kind of ingrained in one of these two somehow. But I think it's probably going to be one of these two. To do some more investigation, let's actually differentiate and set to 0 to find the stationary points. There are other ways of doing this, by the way, including just using quadratic formula a couple of times, which I thought about doing, but it turned out to be a bit messier than this. Factorize out the x, and you find there's a stationary point at x equals 0, which has y coordinate c, so that's good. That's just the point that I was claiming was in my sketch here. And the other stationary point is minus b over 2, plus minus square root of. Now this implies that b has to be negative, because otherwise you're square rooting a negative number. So that's useful to know. I think at this point I can just underline this answer, to be honest, basically. I mean, that's actually what I would do if I was doing the right thing. But just for completion, let's put this value here into here. Now this to the power 4 is just the inside squared, because the half cancels, the power half cancels from the square root. And this thing squared is just this middle thing here. So it looks like this. This ties up to this, which is this. And then we need, for 4 roots, we need these. By the way, of course, this is talking about these 2 stationary points. And we're going to need those to be below the x-axis to avoid this case. So we need this to be less than 0. Move some stuff over. You get this square root both sides, and you need to be either greater than 2 root c or less than minus 2 root c to make yourself square to be bigger than 4c. And of course, because b is negative, that's the exact condition I needed to make d work. So of course, it is still d, which we said it was ages ago. Okay, f is a non-constant polynomial. So it's not f of x equals 3. There's some x term in there somewhere. And g of x equals f dashed of x. F of x has m roots, and g of x has n roots. Which of the following could happen? So counterexamples, or examples. If f of x is x, you differentiate for 1, and then times by x, and you get g of x is also x, which means the number of roots of f and g here are clearly the same. So it is certainly possible that 2 is true. I tried finding more examples and didn't really get very far. So then I started doing the other type of examples and counterexamples, which is drawing it. I don't need to do the algebra, I can just draw it. So let's draw a cubic polynomial with 3 roots. All right, so this is f of x. Cubic polynomial with 3 roots. So m is 3. Now, if I differentiate this, how many roots does it have? And you're saying, well, how do you differentiate it if you don't even have the function? You just have a picture. Well, The derivative of this has the same number of roots as this has turning points, right? The derivative of this function here has a root here because its gradient is 0 there, and it also has a root here. So this function has two roots, the gradient of the function. The f dashed of x has two roots, right? It's got two stationary points, so f dashed of x has two roots. Now, when you times that by x, you're going to introduce a third root at 0, which means this graph here will just be another one of these cases where m and n are the same. They're both going to be 3. Except, what if I just move this graph to the right and make it look like this? Because now when you differentiate this, one of the roots is already at 0. So when you times by x, you're not introducing another root. So this graph has m, this is f of x, and m is 3, but g of x is going to have two roots. It's going to have one here, and this one is repeated. So actually, I found an example where m is greater than n. We have 3 and 2. And finally, if I draw this graph, this is f of x. F of x clearly has one root, but if I differentiate it, it's going to have a root here and a root here, because those are the station points. And when I times by x, it will have a third root in the middle. And so n will be 3, and m is only 1. So that's therefore an example of that, and all of them are possible. Good. Question 20. So we have this very complicated looking integral, I guess. Which of the following must be true? So the integral is 0 only if p is greater than 0. So let's find an example where the integral is 0 even though p is not bigger than 0. So why don't we just go with f of x equals x squared? Because the reason this works well is because f of mod x is just f of x, right? Because when you square something, you're making a positive. It doesn't matter. It's the same thing, right? So this is just f mod x. And so therefore, f of x all squared minus f mod of x, which is the same thing all squared, is just 0. And it doesn't matter what the limits are. The integral of 0 is 0. So I found a way to make I of pq equal to 0 without choosing p greater than 0. So that's not necessarily true. Okay, number 2 then. F dashed of x is less than 0. So the most simple example I can think of where f dashed of x is less than 0 always is f of x equals minus x. Because when you differentiate, you get minus 1. So, okay, there's the function I'll work with here. Apparently this is only if IPQ is less than 0. But the thing is, if I integrate this, I've just chose p to be minus 2 and q to be minus 1, apparently. I mean, that was just a random choice. But again, minus x all squared is just x squared. F of mod x here is just x, right? Because the minus will just go away, so you just square that. And this whole thing is 0. So I found an example where f dash of x is less than 0 for all x, but IPQ is just 0 again. So that's also not necessarily true. And then the third one, IPQ is bigger than 0 only if p is less than 0. So I want p to be bigger than 0 here. And now, the thing is, if p is bigger than 0, then this mod function is irrelevant because you're only integrating across the positive x's because q has to be bigger than p. If p is bigger than 0, q has to be bigger than 0, and so the mod function doesn't do anything. And so this is just 0 again. And so here's a case where basically, if p is bigger than 0, this is definitely 0 every single time, which means that the only way you can possibly be bigger than 0, the only way the integral could ever hope to be bigger than 0, is if p is less than 0, because it's always 0 if p is greater than 0. So I think even though I haven't found a case where IPQ is actually bigger than 0, I think it can only be true if p is less than 0, because the moment p is 0 or bigger, this mod doesn't matter, and you just get 0 every time. So therefore, that one I think is fine, and the answer will be D. Thank you so much for watching, and I'll see you next time.